the last thing we're going to look at with circular motion is motion in a vertical circle. Now this is far more complicated than motion in a horizontal circle, so we're only going to sort of touch on it briefly. In fact, in the IB syllabus, there's no need to do anything more than just sort of look at it qualitatively, not necessarily quantitatively. Now the example that we're going to look at here is a loop-to-loop in a plane. So basically starting off horizontally and then spinning over the top and then coming back down the bottom. So imagine that we have a plane that's flying this way and it's going in that direction with some velocity. The force that's going to cause it to move in a vertical circle, the centripetal force, is going to be upwards, and so that means that the plane will then travel and will end up somewhere over here. So it's now going vertically, and again velocity is now in an upwards direction. Centripetal force is still going to be towards the center of that circle, and then again it's going to start to travel around circular path. It's now going to be upside down as it continues the loop-to-loop. Velocity is now to the left. Centripetal force is still towards the middle, and finally, as we consider as it comes back down again, it's now going to be over this side, and velocity is now down, and the centripetal force is still towards the middle. Now that might look very similar to what we've already seen with circular horizontal circles, and it is in a sense, but it does actually get a little bit more complicated. So if we consider what's actually providing the centripetal force here, it's basically the lift that's being provided by the wings. If we look at this bottom scenario, we can consider though that there's the weight of the plane is going to be acting down. That means that the lift for the plane needs to actually be, let me just move that across, the lift needs to be larger than the required centripetal force in order to counteract the weight. So you can see the lift vector there is quite large. When we go over to the side, it gets a little bit more complicated here in that the weight of the plane is still going to be acting down. In fact, let's just deal with that across all of these scenarios. The weight always acting down in each of these cases. Now, if we jump to the top, actually, that'll probably be the next easiest one to deal with. You can see here the difference between the weight and the centripetal force is this difference at the top here. So we know then that the lift is going to be less in magnitude than what it was at the bottom of the circle. So you can see at the top the lift itself is much smaller than what the lift was at the bottom. Now if we go to the sides, this is where it gets even more complicated. You can see that the weight is acting down, the centripetal force is horizontal, so we're actually going to have the lift being directed at an angle, and then similarly on the opposite side the lift's going to need to be directed at an angle over here. So the lift itself is actually changing quite significantly through the motion of the vertical circle as the plane's moving. But what you can identify then, if you think about lift as being the normal force that's sort of keeping you up, what it means then is that as you move around a vertical circle, the experience of your weight will vary because the lift is changing. So the easiest way to think about that, we'll have a look at in class a couple of scenarios where if you decrease the velocity so that at the top here the lift is almost zero, or the force that's sort of providing the centripetal force is almost zero, so the weight of the object is the only thing that's causing the centripetal force, you can start to get some interesting scenarios to look at in those situations. So in this case, lift is ultimately lift in combination with the weight is providing the centripetal force. And while we're dealing with the motion of a plane, this scenario it's basically the same no matter what situation you're dealing with vertical circular motion. keep in mind here, if we're talking vertical circular motion, what I haven't really identified here is that the acceleration due to gravity in this scenario was always going to be acting down. So if you cast your mind back to the previous video where we were talking about a satellite, vertical circular motion in that case doesn't really make any sense, because it's there's no up or down with the satellite in a sense. It's not moving through the gravitational field, it's moving perpendicular to the gravitational field. So vertical circular motion, we're talking about it occurring within a gravitational field. So if we just consider this again in a bit more detail, let me just go through and label these so I can make some more notes about what's actually happening. So at 1, the lift has to overcome weight. At 2 and 3, so lift has to both has to overcome the weight as well as providing centripetal force, or provide a horizontal force, or horizontal component, let's say. Whereas at the top, so at 4, the lift is actually aided by the weight. So it's not all just the lift doing the providing centripetal force at 0.3. Got that wrong. So at 2 and 4 that should be, and 2 and 3 down the bottom here. So at 2 and 4, lift needs to have the horizontal component, whereas at 3 at the top, the lift is aided by the weight to provide the centripetal force. So one other thing that, or two other things that are useful to note here. Weight's always vertical, and again keep in mind that we're dealing with these situations as simply as we possibly can here. So with weight always being directed down but centripetal force being towards the center, it means then that whatever it is that's really providing, so in this case lift, whatever's providing that centripetal force or contributing to the centripetal force, it means that it's going to change over the motion of the vertical circle. So as a result, motion in a vertical circle is very rarely going to be at a constant velocity. So that makes the analysis even, constant speed. That makes the analysis of vertical circular motion even more challenging because the speed's no longer constant, and so the forces that are acting are going to vary. The centripetal acceleration is going to vary, and so it makes it very difficult. To think about a specific example where it's obvious that that's occurring, I want to have a quick look at a roller coaster. So for a roller coaster, in order to keep the velocity relatively constant, the speed relatively constant, and by relatively constant I mean so that it's not changing significantly, for in a loop-to-loop for a roller coaster, usually it's not circular. So the shape of the loop-to-loop for a roller coaster looks a little bit more sort of that idea where it comes up and then the curve tightens, goes over the top and then comes back down again. So as a result, we don't actually have circular motion here. We might have parts of it, so it might be this first part that's a bit circular, and this is a smaller radius as we go over the top, and increases in radius again. But you can see there that the shape of those loop-to-loops in a roller coaster, they're not actually circular. So by changing the curvature of the track, it allows the speed of the roller coaster to be maintained at a bit more of a constant value as it moves through the ride itself.